Knowledge graph invented by Google is a knowledge base to enhance search engines' results with information gathered from a variety of sources. In our project, we conducted entity recognition and triplet extraction to form a knowledge graph for the OCP company, by which text summarization can be done to generate a useful summary for the management team. The main goals are to identify relevant sentences from the raw ones and to extract relevant entities and relationships, which we will talk later.
The objective of the sentence identification module was to filter out irrelevant sentences from the text extracted from the PDF reports. The relevant sentences were then used to build the knowledge graph. The irrelevant sentences may include sentences that are not from our domain and that do not add any value towards the knowledge graph. Sentences that have been picked up from the headers or the footers, text that belong to graphs and charts that are not relevant to us. Moving on, so for the sentence identification module, two approaches were explored. One was the BERT model and the other was FastText model. So a series of steps were followed and they were as follows. So firstly, to train a model, we need training data. So we manually annotated 3000 sentences as relevant or irrelevant. The next step was to filter out the obvious irrelevant sentences. To do that, a certain set of metrics were defined. They are as follows, like looking at the ratio of digits to characters, ratio of uppercase characters, how many organizations, locations, or countries are mentioned in a sentence, how many non-English to English characters are there in a sentence, and many more. So once the obvious irrelevant sentences were eliminated, the the filtered out data was then used to train the BERT and the FastText model. So moving on to the methodology. So the first step was to train the BERT model using the initially filtered 3000 manually annotated data. So once the model was trained, the model accuracy was evaluated on a held out set of 650 sentences. The data consisted of two classes, relevant sentences and irrelevant sentences. Some sentences taken from news articles from other domains were also added to simulate the effect of irrelevant sentences from other domains. Once the model was trained, it could be used to predict the relevancy of a new sentence. Further, the relevant sentences were then used to build the knowledge graph. On to modeling. So the model which we used was BERT, which stands for bidirectional encoder representations from transformers. So what is BERT? BERT was developed by Google and is based on the transformer architecture. BERT is one of the most groundbreaking developments in the field of NLP in the recent years, and it has performed exceptionally well as compared to its competitors in various NLP related tasks. So, what makes BERT so special? BERT is able to capture the context of the text and hence it is able to address the problem of polysemy, that is, same words having different meanings, which other traditional methods like word-to-vec and glove fail to address. Hence, understanding the context and capturing them is an important aspect of differentiating if a sentence is relevant or irrelevant. So how does word work in our case? So suppose we had example sentences like India orders 10 tons of fertilizers and the second sentence was for more information visit this URL. So the first sentence is relevant to us but the second one is not. So when we feed these sentences to a BERT model, it outputs a contextualized representation of these sentences. These vector representations are then fed to a feed-forward neural network for classification, and the sentences are then classified as relevant or irrelevant. So the whole architecture was fine-tuned on the manually annotated data, and once the model was trained, it can then be used to predict if a new sentence is relevant or not. Coming on to the results, the BERT model performs really well and has an accuracy of 90% on the held-out test set. The F1 score was 0.91 for the positive class and 0.89 for the negative class. As seen from the confusion matrix, it rightly identifies most of the sentences, but we can reduce the threshold to not miss out on relevant sentences that are wrongly classified as irrelevant. To achieve better performance, we can look at more powerful variants of BERT like Roberta, XLNet, etc. And I believe we can achieve better performance with those.
Sentences are the sources for entity recognition, which is the fundamental part of knowledge graph construction. The quality of the input sentences will determine that of the knowledge graph, and thus the text summarization. Currently, we're using SPACY to extract sentences and Stanford Core NLP to filter the sentences. However, the performance is not so good. Therefore, we choose to develop the fox-text model as a comparison of the BERT model. How can we represent the sentences in the computer? Only by numbers. Then vector representation comes out. Traditional methods involve TF, IDF, bag of words, and etc. We first follow the word-to-vector embedding method invented by Thomas Mikolov, as it's used in the context information, especially the order of the words. The pros are that they are context-based and intuitive, while the cons are their subword information is lost and they are unable to deal with the unseen words. Later to say, the calculation is based on back propagation. Incorporating subword information makes the Fox's model more powerful than traditional models. One example on the subword information is given above. The word where is represented by its 3-gram subword, and that this vector representation will be the summation. The Huffman coding tree data structure optimizes the time complexity from ODK to OD log k, where k is the number of classes and d is the dimension. Hashing buckets save the memory with embedding vectors shared within the same bucket. As for the speed, fastest model can train 1 billion words within less than 10 minutes, classify 500,000 words into 300,000 in less than 1 minute. Now, we can see the example further. We add up the subword information for a word and add up the word information for a sentence. The hierarchical classification is based on the Huffman coding tree. In our example, it's just 2 classes here. In this model, we use 9 hand-coded reports and 3,000 extracted sentences. The results above are promising. The fastest model provides high F1 score in the binary classification task. We're expecting to see whether the filtering method will introduce better knowledge graph or not. In summary, the fastest model utilizes the subword information and can deal with unseen words, producing good results with fast trailing speed. As last, we compare BERT and fastest model for their training speed and performance. The BERT model has better performance while the fastest model has better training speed. Once we have more training data, we can do a further comparison. In summary, it's a trade-off between time and performance.
After we filled out the useful sentences, we can begin to construct our knowledge graph. To do this, for each useful sentence, we need to recognize the named entities and the relationship between them. For example, here we have the sentence, OCP exported something to Brazil. In this sentence, the subject is OCP and the object is Brazil. Both of them are named entities, and the relationship between them is export to. So based on this, we can construct a small knowledge graph. There are 2 steps for doing this. The first step is to recognize all the named entities in each sentence, and we use tools like SPACY to help us do that. The second step is to extract the relationship between each pair of named entities. This step is more complicated, and we trained a hierarchical clustering model to do this, which utilizes 2 types of features, the entity type, and the context. This is a flowchart of our modeling process. The input here is the sentences. For each sentence, if there are two or more named entities, we will try to extract the relationship between each pair of them. Then we will construct two types of features. For context features, we use a pre-trained graph model to get the word vectors for each word in the sentences. Then we will use TF-IDF as a weighting factor to adjust it, because some words just appear more frequently in general. After this, we have another weighting factor, the shortest dependency path. We will give more weight to the vector that appeared in the shortest dependency path. This is an example of how we could get the shortest dependency path between two named entities. Firstly, we use BASIC to extract the syntactic dependency relationship between the word tokens. Each token will be a node. If there exists a dependency relationship between the two tokens, there will be an edge between the two nodes. Based on this graph, we can find the shortest path between two named entities. In this example, the path in red is the shortest dependency path from OCP to Brazil, and the path in blue is the shortest dependency path from OCP to US. Going back to our model, another kind of features is the type of the subject and object. The types could be organization, person, location, etc., and we also encoded them as vectors. Then for each type of vectors, we conducted PCA to reduce some dimensions. Finally, a hierarchical clustering model is trained to group the samples into clusters. The entity pairs in the same clusters are expected to have the same type of relation. Then for each cluster, we use the most frequently appeared words in the dependency path as the representative of the relation. So we get the subject, the object, and the relationship. Now we are able to get the whole knowledge graph.